right, guys, another great production at B102. All right, so in this production, I'm going to talk about inclined planes, but I'm going to do some of the problems. So in the last video, I talked about the theory. So I showed you how to write the equilibrium statements. In other words, how to write your F net equals ma, both horizontally and not horizontally, but up the ramp or down the ramp and perpendicular to the ramp. So now I'm going to start doing some problems. It says a box weighing 562, so that's the mg basically, right? So if you want to find the mass, you'll have to divide that by 10. The incline forms 60-degree angle with the horizontal. Find the components of the weight parallel and perpendicular to the plane. So in this question, they're asking us to find the parallel component in magnitude, parallel component of Fg, and the perpendicular component of Fg. So first thing we want to do is draw a free body diagram. So here's the object, mass m, which we can see that is 56.2. And forces acting on this are the weight of it. So that's your mg. Now keep in mind that this mg can be broken down into a y component, okay, perpendicular to the ramp, and an x component parallel to the ramp. And you have your Fn that's no longer going straight up towards the ceiling, towards the top of your paper, Fn. Now, since this is a frictionless surface, the object has no choice but to accelerate. And those are the only forces acting on this. So this angle here is 60 degrees. If I continue with this line that's perpendicular to the ramp, this angle here is also 60 degrees. So to find the F parallel, that's going to be your mg sine of 60, and that should be 562 sine of 60, and you got an answer there. Perpendicular component would be your mg cosine of 60. So you have to kind of like make a triangle here. Here's your parallel component, here's your perpendicular component, but make sure you erase those after you're done. You're not supposed to have the components of forces on the free body diagram, because those are not real forces. And you do the same thing then. Find the acceleration. So to find the acceleration, we have to work along the ramp. And since the object is going to slide down the ramp, I'm going to look at down as positive. So the only force I see, or component of a force that I see acting down, is the mg sine of 60. So in other words, I'm doing F net in the x direction equals ma in the x direction. So that leads me to this. Mg sine 60 equals ma, right? And you can see that I did not have to give you the mass to find the acceleration, but I had to give you the mass, or at least the weight, to get the parallel and perpendicular components. So this just leaves us a equals g sine 60. So it's 10 sine 60. And this is a nice shortcut for multiple choice questions. If you don't have friction on a ramp and the only forces acting on it are the weight and the normal force, your acceleration will always be g sine of the angle of the ramp. Okay, so that's only if you have multiple choice questions. If not, you have to show this word. Find the normal force. Well, the normal force is here. That must equal the perpendicular component of mg, because this object never leaves the surface. All right, so let's look at the next one. And we're on page 37, by the way. I'm going to try to save this free body diagram so I don't have to redraw it all the time. I'll just change the angles here. So this is a 35-degree angle. So the weight of this object is 180 newtons. Okay. It's on a hill that makes an angle of 35 degrees with the horizontal. So the ramp makes a 35-degree angle. Find the acceleration of the wagon down the hill if the coefficient of friction is 0.65. Now dimension in friction, so the object is going to go down the ramp, which means friction is up the ramp. Okay, so I can see that what's trying to make me go down the ramp is mg sine of 35. In other words, I'm doing F net equals MA in the x direction, which means down the ramp, minus the force of friction equals MA. Here, I don't think I had to give you the FG. I don't need to know the mass. It could be just an object of mass M. And then the reason I'm saying that because there will be problems that don't give you the mass. And if it doesn't give you the mass, you should see that the mass should cross out algebraically somewhere. So this is mg sine 35 minus. Now I know that the FF is mu Fn. So it's mu Fn. And Fn is the same as the perpendicular component of the weight, which is the adjacent in this triangle here, because this is the 90. So this angle here is 35. This is the mg. That's got to be the adjacent with respect to this 35-degree angle here. This is 35 degrees. So mu Fn, which is mg cosine 35 theta, equals ma. So even if I didn't give you the mass, you should be able to solve. And the answer for that is 0.41. Yeah. So if we do the math here, we get 10 sine of 35 minus 0.65 cosine of 35 equals. So let me just try it quickly, make sure. So sine of 35 minus 0.65 cosine of 35 let me try that one more time. I think I'm doing something wrong. Sine of 35 minus 0.65 cosine of 35. Oh, I didn't do the minus before. Okay. Sine 35 minus 0.65 cosine of 35. Right, and then times 10. And I should get 0.41 meters per second squared. All right, let's look at the one under 56. Okay. 120 kilogram sled is being pulled up a 20-degree ramp. Snow-covered slope. With a constant speed, with a force parallel to the incline. So a couple of things we have to pay attention to here. We're going at a constant speed, which means no acceleration, and we're pulling with a force F applied, or you can call it tension, or you can call it whatever. Because if you're pulling with a rope, you probably can call it tension. Determine the tension in the rope. So maybe since it's talking about tension, I'll just change this and I'll call it tension. So F net equals MA. Now, this time I'm going to look at up the ramp as positive because I'm moving up the ramp. So it looks like it's T, anything that's parallel to the ramp, minus this component of mg, which is mg sine of 20, equals ma. Now, they're telling me that we're going at a constant velocity, so this has to be 0. So your T would just be mg sine 20. So it would be 1200 sine of 20 degrees, and your answer should be 410.42 newtons. Then what's the normal force? To find the normal force, you just have to go in the y direction, this direction here. So the normal force has to equal the perpendicular component of the weight. So Fn is mg cosine of 20 degrees. So that's 1200 cosine. 1200 comes from 120 times 10. Cosine of 20, and you should get 1127.63. All right. Next question, 57. I'm going to redraw this here. A force of 180 newtons parallel to the incline is required to push. So instead of pushing it from the bottom, since we cannot have forces going into an object, I'm going to pull it from the top. What I mean is, like, instead of pushing from down here, I'm going to pull from here. Okay? And I'm going to say that's an applied force. Okay, this is my mg. This is perpendicular to, no, not quite. So this here is the perpendicular to the surface, to the ramp. And it looks like we have some friction. So if we pulling up the ramp, friction must be down the ramp. Okay, so if I'm moving up the ramp, I'm going to look at up the ramp as positive. And this mg can be broken down into its components. So just when you're doing the components, and which you have to erase later, this y component, this perpendicular component, in other words, has to be along, lined up with the Fn, which is here. And this parallel component has to look kind of parallel to the ramp. That's why we call it parallel. And the other one has to be, looks perpendicular to the ramp. That's why we call it perpendicular. What's the mass of the wagon if the coefficient of friction is 0.6? All right, so I'm going to do Fnet as MA. Now going up the ramp, I see Fa, that's trying to make me accelerate up the ramp, minus, okay, anything that's holding me back. So I see FF here, and I also see the the parallel component of mg minus mg sine of theta, which is 15 degrees. So this is 15 degrees. That's 15, this is 15. I showed you in another video using a little geometry proof that they're the same. Now we're going at a constant speed again, so which means there is no acceleration. This is 0 here. So the Fa is 180, Ff is mu Fn, and Fn is the same as this perpendicular component. Okay, so that's mg cosine of 15 minus mg sine of 15 equals 0. So if we manipulate this a little bit, so what should we get? So you have the mass. No, you don't have the mass. We're looking for the mass. So it's going to be 180 minus. Now this is 10 times 0.6, so that's 6 cosine of 15 times m minus 10m sine of 15 equals 0. So maybe we can move. They can equal here, put a plus here. Factor out an m. Okay. I hope you can follow the algebra here. And you just pretty much calculate what's in between these brackets and put it under 180, and you should get 21.47 kilograms. Okay. 58. So the object weighs 686. So that's the Fg. That's, in other words, that's the mg. Slides down. So we're going to look at down as positive this time. I'm going to change that. Okay. 10-degree ramp. Okay. Frictional force acting on it is 14 newtons. So this is no longer applied. So I'm going to say that this is the force of friction. What is the acceleration of the sled? Okay, so there's no friction here. And make sure you erase this perpendicular and parallel force. I must have said that at least a dozen times by now. So if I'm going down, my Fnet is MA becomes the forces acting down the ramp trying to make you go accelerate down the ramp is the parallel component of mg minus any friction that's trying to hold you up, hold you back, equals the mass times the acceleration. So this is going to be the mg is 686 sine 10 minus friction is given as a number. They're not talking about coefficient of friction. It's just 14 equals the mass, which is 686 divided by 10. So 68.6 times the acceleration. And if you put that in your calculator, you should get an acceleration of 1.53 meters per second squared. All right, 59. You can see that they are all similar. You just have to be careful about what kind of forces you're dealing with and in what direction you're traveling. So it's all a repeat. Okay. The crate slides down an inclined plane with a constant speed. So you have to pay attention to words like that. So which means no acceleration. The plane is angled at 30 degrees. So this is 30 degrees here. What is the coefficient of friction? So it's got to be some friction here. Okay. Because if there was no friction, there is no way that it will go at a constant speed. You have to have something that will match up the mg sine theta. That's the bottom line. So that's dynamic equilibrium. So mg sine 30, and this is obviously after you write F net equals ma, which is mandatory, right? Minus force of friction equals ma, which is 0. Now, it doesn't give us the mass, so hopefully with the algebra we can eliminate the mass. So it's m, well I can do 10m, I can just start putting some numbers in there. So 10m sine 30 equals, I'm going to just move the ff to the other side, that's mu fn. Now fn and the perpendicular component of mg must be equal. So that's mg cosine of 30. Actually, I didn't have to do this. This is mg, so I can see that the m and the g go away. Right? So the mu kinetic, that is just tangent of 30 degrees. And I showed you this in the first video. Okay? So I said that mu is the tangent of the angle. And if you do the math there, you should get your answer. Okay, we're looking at number 60. The coefficient of friction between the metal block and the inclined surface over which it slides is 0.2. Surface makes an angle of 20 degrees. So I'll change this to 20. With the horizontal. And the block has a mass of 80 kilograms. So for now, just call it M, and we can plug in the number 80 kilograms later if we need it. What force is required to slide the block at a constant speed up the plane? So now up is positive. So here is an applied force, and friction is going back. Right? So FA is trying to move you up the ramp. FF and the mg sine theta and gagging up on you to hold you back. And up is positive here. And again, it says constant speed, which means there is some equilibrium here. So I'm going to write my F net equals ma, or the sum of the forces up the ramp and down the ramp equals ma. So it's going to be Fa minus force of friction minus this component of the weight, which is mg sine of 20 degrees, okay, equals ma, well, the acceleration is 0. Okay, so we're trying to find this Fa basically. So Fa equals, I'm gonna do multiple algebra steps at once. So Ff and the mg sine theta are gonna be added to the other side, to both sides basically. So it's mu Fn, which is mg cosine of 20. So it looks like I have no choice but to use the mass this time. It's not going to cross out. So the mg should be 800. So it's 80 times 10 plus 800 sine of 20 degrees. And if you do the math here, you should get 423.97, so about 424 newtons. Number 61. A car accelerates down an incline, so now down is positive. The angle is 30 degrees. Coefficient of friction between the crate and the plane is 0.30. So friction is up the ramp now. So I have to erase this. Find the acceleration of the crate. Now the acceleration is going to happen down the ramp. So I have to do my F net equals ma down the ramp. So I see that mg sine 30 is making you go down the ramp, but ff is holding you up the ramp, and that's equal to the mass times the acceleration. Now they don't give us the mass, so hopefully the algebra will help us eliminate it. So this is just 10m sine of 30 minus ff is mu, which is 0.3, times fn, which is mg, that's mg, or mg, cosine of 30 equals the mass times the acceleration. And we can divide everything by m, and we'll get an acceleration of 2.4 meters per second square. We're at number 62. An object that has a mass of 50 kilograms is pulled with a force of 400 newtons on an inclined plane. The coefficient of friction is given. The inclined plane makes a 30-degree angle with horizontal. So we're assuming that we're pulling at a force that's parallel to the ramp. It doesn't say that we're pulling at an angle. Right. So Fa is there. Friction has to be holding you back, trying to hold you back. And the angle is 30 degrees, just like before. What's the acceleration? So now up is positive this time. Up the ramp is positive. So I'm going to do my F net equals ma. So I see that the applied force is acting up, okay, minus the force of friction holding you back, but also the mg sine 30 is holding you back, and that's equal to m times a. Now the Fa is 400. The Ff is mu, which is 115 times Fn, and Fn is the perpendicular component of mg. Later on, that's going to change. It all depends on the picture here. It depends on the free body diagram. So 115 times mg, which is 500 cosine 30, okay, minus mg, which is 500 sine of 30 equals the mass, which is 50, times the acceleration. Now, how you do this in the calculator, that's your business. So the answer for acceleration should be 1.70. 1.70 meters per second square. Now it says starting from rest, how long will it take to pull it 10 meters? So up the ramp. So basically, the acceleration is the link between kinematics and forces. So your acceleration is given, or a pound. Okay, we're starting from rest, so the initial velocity is 0. Okay, we have a displacement of 10 meters up the ramp, and we're looking at time. We're looking for time. So I think I have to use the one that doesn't have the final velocity in it. So delta x is v initial t plus half a t squared. So delta x equals, this is gone, so it's going to be 1/2 times 1.7 times t squared, And maybe I should replace this delta x with 10. Okay. And so it's 20 divided by 1.7, and you have to take the radical of that. All right, we're looking at 63. Now 63 is a little different because now you're pulling up the ramp, but you're not pulling parallel to the ramp. You're pulling up the ramp at an angle with the ramp. So let's see how that looks like. Let's see what that looks like here. So you have the mg down here. Okay, here's your surface that's perpendicular. This line that's perpendicular to the surface. Now we have a mass m. We'll just call it m for now. Now the ramp, the mountain makes 15 degrees with the horizontal, and then you pull in up the ramp with a force Fa, I guess. And if you're using a rope, you're using a rope, so maybe I'll just call that tension, okay? And this angle here that you make with the ramp is 10 degrees. That the force makes with the ramp is 10 degrees. Okay. The coefficient of friction is that much. Okay, so we're pulling up the ramp, so friction is down the ramp. And I'm going to choose up the ramp as positive. And I think those are the forces acting on this object. And obviously we have Fn. Okay, the object never leaves surface of the mountain. All right, I think we're good to go. Starting from rest, how long will it take to pull the person 50 meters up? So that's a hint that you have to use dynamics to get the acceleration first. So I'm going to try to see what I can do up here, up the ramp. So up the ramp, T is pulling up the ramp, but it's also pulling perpendicular to the ramp. So I only concentrate on the x component of T, this one, and we're going to erase this later. So that should be T cosine of 10 degrees, just like what we did with the forces at an angle in the past. What's holding me back? It looks like friction is holding me back, and also parallel component of the weight is holding me back. Now just be careful which angle you put in there. In here, you have to put the angle that the mountain makes with the horizontal. Equals, now we have to say either MA or 0. But here it says that it starts from rest and it accelerates to a certain speed, so it's got to be some acceleration. Okay? All right, so let's see if we can plug in some numbers there. So it's 800 cosine of 10 minus. Now you have to be careful with the friction. So force of friction is mu Fn. But Fn is no longer equal to the perpendicular component of the weight because there is an extra piece here, okay, that's acting perpendicular to the ramp. So this is like your T in the y component of T. This was the x component of T. So if you look at it this way, going up, you see that there is a Ty, which is really T sine of 10. And the normal force is also acting up this way. They're both acting up that way, so that's Fn equals the perpendicular component, which is acting down. So that should be equal to the perpendicular component. So which makes the Fn the difference of these two. So the perpendicular component is just mg cosine of 15 minus T sine of 10 degrees. And you should get 0.1 times, now that's 80, so this is 800 cosine of 15 minus the T is just another 800, okay, sine 10, and let me see if I have the force of friction here. I don't have that, but we can take that force of friction and put it in here. Whatever expression, whatever number we get, we put it in here. Okay, minus the mg, that's 800 sine of 15. Now this is a number. This hashtag is a number now, right? Equals m, which is 80 times acceleration. Now you get your acceleration, and that should be 6.47 meters per second squared. And then you would do your kinematics to find the time. It's just like the previous one. So you have to do the equation that doesn't have VF in it. And you should get a time of 3.93 seconds. I'm going to continue this video in a little bit. So for now, just hang in there. All right, we're on number 64. So again, it's still an inclined plane. So a ball is rolling up a hill. So I'm just going to do ball as a box, right? With an initial speed of 20 meters per second, the coefficient of friction between the ball and the hill is given, and they give telling us that the angle is 30 degrees. How long does the person have to go to get out of the way of the bowling ball when it comes back down towards him? So what I think we should do here is find the time it takes to get to the top, and find the time it takes to get to the bottom, and we're going to see that those times are not equal, and we'll make that decision once we draw the free body diagram. So I'm going to put the object up here, and here is the mg, and here is the perpendicular line to the incline. And so initially it's going up the ramp, but there is no applied force on it. So it's just going to go up because of inertia, but the mg sine theta is trying to hold it back. So eventually it's going to come to rest and come back. So let's do it on the way up first. So up. We have the normal force here, and we have friction down. So now we're traveling up the ramp. So I'm going to do the work for up the ramp here. So there is no force pushing it up the ramp. So the only forces that are acting on it is the force of mg sine theta and the ff. So it's going to be negative mg sine 30 minus the force of friction, and that should equal to ma. Right? And here we're not given the mass, so hopefully we'll cross out somewhere. So this is negative 10 m sine 30. Now ff is mu, which is 0.2, fn, which is m, which is mg, that's 10m cosine of 30, equals the mass times the acceleration. And you can divide everything by m, and you should get an acceleration equal to negative 6.73, and it's understood because he's slowing down up the ramp, which happens to be the positive direction. Okay. All right, so now we have to figure out the time it takes to go up the ramp. So we have to use, we don't know what distance it travels, so we're going to use the v final is the v initial plus acceleration times time. When it reaches the highest point on the ramp, it's 0, and the initial velocity was 20, and the acceleration is 673 times t. So the time up the ramp is equal to 2.97 seconds. Now let's see if we're going to get an expression similar to this, F net equals ma, coming down the ramp, and if the time is actually going to be 2.97, or is it going to be more or less? Now, coming down the ramp, I'll draw another one here. You still have your mg acting down. It's 30 degrees. You have your fn.
in this direction, and friction is up the ramp. Right? Now, since it's coming down the ramp, this is positive. Now, the statement should be mg sine of 30 minus the force of friction, which is mu Fn equals ma. Now, the magnitude of this net force when you're going up the ramp is bigger than the magnitude of the net force when you're coming down the ramp. Because if you think about it, when you're going up the ramp, both the mg sine 30 and the ff are ganging up on you to hold you back, to decelerate you. In here, only the friction is trying to hold you back. So the acceleration down the ramp should be less. It's going to be a positive number, but in magnitude, it should be less than 6.73. So let's see how much it is. So the mass, so this is going to be 10m sine of 30 minus 0.2 times mg cosine of 30 equals the mass times the acceleration. Okay, and you should get an acceleration equal to 3.27 meters per second squared. And I hope you understood this conceptually, that the magnitude going down the ramp is going to be less than the magnitude going up the ramp. Again, because up the ramp, you have two forces trying to hold you back. Okay, and nothing trying to make you go up the ramp. It's just your inertia is keeping you going. Coming down the ramp, the mg sine theta is trying to make you go down the ramp, but only the force of friction is holding you back. So the net force in going down the ramp has to be less. All right, so, and we do the same thing here, and we get a time equal to 4.26. Actually, the problem is that we don't know with what speed it's going to have at the bottom of the ramp. So I don't think we can use same equation as before. So let's see what equation we can use. So we're looking for the time down the ramp. We have the acceleration, and we have the initial velocity at the top as being 0. Okay? And that's pretty much all we have. So we don't have an equation that can link those. So what I think we should do is maybe find the distance first, and then find the time. Yeah. So I think we can use the equation that says v, can maybe use delta x equals, so we can get that probably from the previous part here, because it's going to go up the same distance that it's going to come down. So that's what we should do. So I think we should come here and get the distance. So we can say delta x is half the initial velocity plus the final velocity times the time to go up. Yeah, that's what we should do. Delta x is half. This is 20. The final velocity is 0. And the time is 2.97. And we should get a distance equal to 29.7 meters. So now we can use that here. Delta x is 29.7 meters. Now I think we can use, which equation we use? We use the one that has the time square. So delta x equals v initial time times time plus 1/2 a times time square. This is gone. You're looking at it from the top down. So you're starting from rest, and you can get your time to be 4.26 seconds. Okay? Because now you're accelerating at a lower rate that you were decelerating before. So it's going to take longer to come down. All right, looking at 65. coin is placed on the cover of a book, if a book begins to move when the cover makes an angle of 35 with the horizontal. So I think I did this in the first video. So you have your mg. The mass is not given, so hopefully we'll cancel out somewhere. This is 35 degrees. And you have some friction here. So this is your maximum static friction, right? So any angle above 35 will just start to slide. Okay. So at this point here, there is no acceleration. So we're going to say that mg sine of 35 minus this maximum static friction equals 0 just before you move. All right. So mg sine 35 minus mu static times Fn, which is mg cosine of 35, equals 0, so which means these two quantities have to be equal. And we can cross out the mg's. And you can see that the coefficient of static friction is equal to the tangent of 35. All right, the next one. I think I have 65 listed twice, but so the second 65, I guess. All right, so instead of having this force down here, I'm going to put it up here. Kind of like parallel to what I have here, so. Okay, that's close. All right, so I'm going to pull up from here. So here's my applied force. And the angle that I make with the ramp is 50 degrees. And I still have my mg going down. Here's my y-axis. This is 18 degrees. Is my normal force. And so we're going down. We're going up or down? Okay, we're going up the ramp. So up is positive. And the applied force is given. That's 2800 newtons. Just put it here. Now we're moving at a constant velocity, which means there is no acceleration. So we're trying to find the coefficient of kinetic friction. All right, so let's try this. So if you're going up the ramp, friction has to be going the other way. So I'm just going to write it as lowercase f. And I think that's all the forces there are, right? So now Fa cosine 50, this component here of Fa, this one, is trying to make you go up the ramp. This one is weakening this contact between the tires and the ramp. So it's going to be Fa. I'm writing F net equals Ma going up the ramp. So it's Fa cosine of 50 minus force of friction minus the parallel component of mg, because it's pointing down, mg sine of 18 degrees equals ma, which is 0. All right, so this is 2800 cosine of 50 minus, now the force of friction is the mu that we're looking for times Fn. So now you have to be careful with the Fn. Now the forces going up in that direction, right, must equal the forces going down in this direction. Well, you have the perpendicular component of mg. So we see that Fn plus this component, which is Fa sine of 50, those two should add up to equal the perpendicular component of the weight. So which means Fn must equal the perpendicular component, which is mg cosine of 18, minus Fa, which is 2800 sine of 50. So maybe we should figure this out first and then come back and plug it in here. So this is going to be 400 times 10, so that's 4,000. We can do the math actually, one shot. So this is 4,000. So 4,000 cosine 18 minus that, so you get an Fn equal to 1659.30. Minus minus 4,000 sine 18. That's the mg. That's equal to 0. Now you just have to you figure out how to do the algebra, and you should get 0.34. So your kinetic friction, the coefficient of kinetic friction is 0.34 with no units. Okay. If you go a couple pages, if you go to number 68, it says to try number 66, but this time pushing down on the curve. So I'm going to do number 68 first. Okay, so it should be, instead of pushing up this way, we're pushing down this way. So I'm just going to come and I'm going to put that force here. So this is my FA, and this is my angle of 50 degrees. Yeah, and nothing else changes in the up the ramp, but I think here there is a change. So the statement is still valid, except here there's a change. So it's still your x component of FA is going up the ramp, but your y component is going down this way instead of going up like before. So it should be Fn is equal to this component of FA plus the perpendicular component. So it should be a plus here. And if you do the math, you should get an Fn equals to 5949.15. Okay, and all the other numbers should remain the same, and your coefficient of friction is just 0.095 with no units. All right. This is an introduction to number 67 on page 42. If you have a pulley here, and you have two objects on two ramps, so you have two inclines, and you have two angles here. You have theta 1 here, and let's just say theta 2 here. So this is object 2, and this is object 1. And you want to figure out which way this whole system will spin. So I think we should come up with like a quick way to figure this out. So let's just look at all the possibilities. Let's make the prediction that it's going to go to the right. And let's write our equilibrium statements. So here are the forces. This is the mg. If it's going clockwise, friction is down on this one. I'll call it F1. This is M1G. This is M2G. Here's the normal force on 2, the normal force on 1. And if 2 is going down, the friction on it will be F2 going down. Will be some tension in this cable, and it will be some tension in this other cable. So what's trying to make you accelerate is M2G sine theta 2. What's holding you back is the friction on this number 2, and also the friction on number 1, and the parallel component of M1G on the other side. And you're trying to accelerate both objects. Okay? Now let's look at it the other way. Let's say if it's trying to go, this is clockwise, this is counterclockwise. If it's going counterclockwise, it will be M1G sine theta 1 minus F1 minus F2, and the parallel component of M2 is trying to hold you back, and it's still accelerating both objects. So basically I wrote F net equals MA in both cases. So if you notice, both possibilities have minus F1 and minus F2. So if I take those expressions or those terms and I move them to the right side. Okay? Now, this quantity here is positive, and this one also is positive, right? So basically, to figure out which way it's going to go, it comes down to comparing the mg sine theta on each side. So if the mg sine theta for 2 is greater than 1, it will go clockwise. If m1 g sine theta 1 for block 1 is greater, then it will go counterclockwise. And that's how you make a decision about which way to go. So now let's do the problem. The only force that wants to make me accelerate is m2g. I'm writing my F net equals ma now, right? Minus, oh yeah, and there is friction here. So if this one is traveling up the ramp, the friction is back. Okay, m2g minus friction minus m1g sine of 37. That should equal to ma. So we have the masses, we have the g. So I think if we can figure out what the friction is, we're pretty much done. So the force of friction is mu times Fn. And that's going to be 0.23. And the Fn is m1 g cosine of 37 degrees. Right? So the force of friction, which I didn't calculate here, yeah, I didn't calculate that, but you can always do the math here because you have everything. And the only difference is that this mass here has to be the combination of the two. Okay? And you should get an acceleration equal to 4.05 meters per second squared. If we have gone, what do you call it, clockwise, we'll find that there is an contradiction. So the trick here is like, you probably need to find m2g, m1g sine theta, and f, and do some comparing to figure out which way you're going to go. Maybe we can talk about that in class. Now to find the tension, I'm just going to pick either block 2 or block 1. I think it's easier to pick block 2. So because I don't have to deal with this incline. So with block 2, it should just be m2g minus the tension in this rope here. That should equal the mass of block 2 times the acceleration we found earlier, which means the tension is m2, which is 16 times 10 minus 4.05. And that should give us 95.23 newtons. All right. Q and Bernard want to be in the video, so I can't say no to them. So here they are.
How you doing?
All right. Say hi and say bye.
Hi. Bye.
All right.
Please, guys.
All right. So we're on page 43. Okay. So we're looking at this number 5 here. Now, if you read it carefully, it shows you that the acceleration is in the negative direction, which means down the ramp. So the object is moving up the ramp, but the acceleration is down the ramp, which means it has to be slowing down. And it's slowing down at a rate of 0.5 meters per second. So that's negative 0.5. So if it started with 2 meters per second, it's going to take 4 seconds for it to lose all of it. So after 5 seconds, it's already on its way down. Okay? So it's on the way down and it's speeding up. So the answer should be D. So we don't have to do any math there. So let's look at the next one, so which is the RT16. All right. So what's wrong with this picture? Okay. So there is definitely a tension by the rope. There is a normal force. There is the weight. But here's the problem. Okay. It says friction of F. Basically, they're talking about the friction on the incline by the box. We don't care about the forces that the box exerts on its surrounding. We only care about the forces acting on the box. So that should be replaced with the force going the other way, and it should say F on the box by the incline. And you can look at the answer key and you can see more detailed answers. Okay, 2 blocks. So you have 2 blocks, one on a flat surface and one on a ramp. So this person is saying that I think the normal force is the same in both cases, which is not true. Now, in the first case, the normal force is equal to the mg, because you only have to support the mg. In this part here, you only have to support part of the mg, one of the components of the mg, which is the perpendicular component. And for all vectors, components are always smaller, or any of the components is always smaller than the vector itself. Okay, so in this case here, the normal force when you are on the ramp is less. All right, this one is a little tricky. Number 18, RT 18. So when you push in down at an angle like this compared to pulling, so if you push in, you also push in down vertically, so which means your normal force goes up. And if your normal force goes up, your force of friction goes up. And if you want to maintain a velocity of 2 meters per second, it means the x component of F has to be bigger in the first case than it is in the second case, because in the second case, your Fn goes down, which means the friction also goes down. So with the tension here, with the second case, case B, you don't need a lot of force to maintain a constant speed. Here, you need a greater force because your friction is bigger. So the F is greater than the T. Number 19 is kind of like the same thing, except now one is at an angle and one is not. So when you pull in down like at an angle like this, you're making the normal force go up, which means the force of friction also goes up. When I say it goes up compared to case A. So if the force of friction goes up, this x component, right? Okay, this x component of the tension in the rope has to be greater than the tension in here. Okay, because you want to maintain a constant speed. And if this x component is greater than this force, well, the resultant here, which is the actual tension, is always going to be greater than one of its components. So the tension is greater than this Tx, which in turns it's greater than the tension in cable A. Okay, and the last one, and we've done a lot of this in class. It says, is the tension, basically it's asking us in which string is the tension the greater. So all you have to do is figure out which cable is closer to being vertical. So this one here is a 60-degree angle. You can do alternate interior angles. This one is 30 degrees, right? So string 1 is closer to being vertical than string 2, and you can see it in the picture. So which means that string 1 has to handle more of mg than string 2. All right? So now I have the soccer team with me here. So they want to say hi. Yeah. So you guys want to come and say hi? Who wants to come and say hi?
Me again.
All right, me again. There you go. This is Quinn.
Hey guys.
All right. By the way, they just won the semi-final yesterday, right?
Boy.
Final against Ramapo. This is Big Joe.
Big Joe.
Big Joe.
Jolie.
All right.
We made varsity.
This is Oxy.
Varsity, baby.
This is the Paulo. Who else
Quinn.
is here? Kieran.
Quinn
Oh yeah,
Joseph.
Kieran is here. Yeah, you.
No one cares about Kieran.
Q. You're Q. See, you see 2 Qs in there.
That's awesome.
We got Jiho.
What is Gio?
Jiho's like
Gio doesn't want to be bothered. He's sleeping. All right. See you later. All right. I'm out. Peace.